So the Syrene song of certainty, and by that I mean the lure of what we think we know, the comfort of the accepted wisdom versus the fear of not knowing. We have to recognize that this love of certainty is a very innate and undeniable human attribute. It would be disingenuous, if not foolhardy, to propose that there's some group of humans somewhere, somehow, that are somehow immune to or above this love of certainty. It's an integral component of our collective psyche. Now, it's an accepted, it's a rather common feature of these certainties that they don't even really have to be very predictive. In fact, some of these certainties can be very difficult to shake, even in the face of repeated and inconsistent and contradictory observations. In fact, as I've pointed out before, humans tend to see what they believe, not believe what they see. Now, this love of certainty goes back a very long way. In our very earliest days, we clung to the certainty of things to fill the darkness beyond the campfire. And we began to construct answers to these questions that attracted us like moths to a flame. Where did we come from? Where are we going? And what is it that holds up and populates the sky that's so full of stars above us? And in the long tenure of human history, we've answered those questions with absolute certainty, many times, and in many forms, in a dizzying array of different kinds of explanatory frameworks. And every time, in every case, thousands of us, hundreds of thousands of us, millions of us, creative, insightful, and intelligent beings that we are and always have been absolutely certain that we're right. Until the tide of history shifts and we find something else to be absolutely certain about. And that's just one of those things about being human, and we might as well just get used to it and try to manage around it. And to a certain extent, science is our attempt to manage around it. It's our coping mechanism for this love of certainty. We replace certainty with testable hypotheses, beliefs with falsifiable theories. But we are only human, after all, and we're so susceptible to that Syrene song of certainty. You would think that after thousands of years of being so certain about so many things that are wrong, we would be a little more careful about being certain about anything. But we fall for it every time. We can't help ourselves. We're certainty junkies. In the language that alert you to the creeping influence of certainty in science. Now, certainty, of course, is a barrier to the open mind. It blocks us from really seeing and re-observing. So there are certain words that we need to be cautious about, and these are words like surprise and unexpected and impossible. All of these are red flags. And they're a dead giveaway that the observer has a clear bias towards what they expect to observe. They're not testing hypotheses. They're not weighing competing models. Their intention is to make observations to confirm what they think they already know. And if the model is not that predictive, then they end up getting surprised a lot. So much so that surprise becomes unsurprising. And there's actually a fair amount of surprise that you see in the reports coming from astronomy and cosmology. A lot of that surprise surrounds high redshift objects. And a lot of the surprise comes around the relationship of the proposed dark matter and what we see. So let's begin actually with dark matter. Now, the lambda cold dark matter model has a rather elaborate mathematical superstructure, but ultimately it's all poised on a couple fundamental, certainties. And those are that gravity, one, is the dominant force, only force, in the formation and structure of the universe. And two, cosmological redshift is a reliable indicator of distance in the observable universe. So I'm going to focus on these two foundational certainties to see if maybe we haven't again succumbed to the Syreni song, or orbital velocity assumes that gravity is the only force at work. So as long as gravity is the only tool in the toolbox, then there's going to be the need for the ad hoc addition of some extra matter to sort of make up the difference. We need to balance the books, gravitationally speaking, and dark matter sort of fills the bill. But what if that primary assumption is incorrect? What if it's not the only force at work? Well, the electric universe theory, of course, proposes that there are large-scale current-carrying plasma filaments that are acting, and that actually this flat rotation curve is rather consistent with an electrically driven homopolar motor. But gravity continues to dominate our thought process in the cosmological sciences. The reason for this is actually worthy of an investigation unto itself, and it has to do with the glamorization of gravity, with the idolization of Einstein, and the subsequent rise in status of the mathematical and theoretical physicists in the mid-20th century. But as long as gravity is seen as the only force shaping and driving the universe, we're going to continue to run into these inconsistencies and surprises and unexpected observations with cold dark matter. The quantity and quality of these observations preclude them being the serendipitous alignment of these objects in our field of view. There's something else going on. So you would think that observations like these would shake our certainty in redshift, but they don't. And our ongoing certainty about redshift as a cosmological yardstick will continue to yield surprising and unexpected observations of impossible cosmological objects. So let's look at a few of these impossible cosmological objects. There's impossible galaxies, impossible quasars. And they all have sort of a common theme. They're impossible because they're too massive, they're too energetic, they're too extensive for the redshift that they're at. They can't possibly have formed within the time that they had after the Big Bang, because being high redshift, they're much nearer to the time of the Big Bang, in theory. It's extremely energetic. Since gravity is the only force available to us, since it's the only force, you need supermassive black holes, but it's far away, so how can you form such a supermassive black hole when it's so far away and it's so close to the time of the Big Bang? It becomes logically inconsistent and will continue to break down, and more unexpected observations like this will be made. I should mention that what we see is, I'm swiping, is this. We don't see that. That's an artist's conception. And a good illustration of something that I mentioned a while ago about this viewmaster of belief, this thing that we hold up that sort of interferes with our ability to see what's really there. But now that I think about it, and I think of all the supercomputers and the virtual reality that we build around universes constructed around the cold dark matter model, it's really more of a virtual reality headset of belief. And as long as we continue to sort of rely on these certainties and build these virtual realities of universes, we'll continue to be surprised by the unexpected observations when we actually go look at the real thing. The observers commented these observations should overturn our long-standing theories. But that was only true. Instead, what happens is we retreat to computer modeling and the supercomputers to readjust the parameters and to change our virtual reality. So much so that, as Tim Rees from Universe Today pointed out last year, the cosmological standard model sort of becomes like a Rube Goldberg device. Well, how did we get here? How did that happen? Why is it that there are so many exotic things like dark energy and dark matter and black holes? Why is the fanciful become commonplace, and the commonplace, like current flow in a plasma, which is like in a fluorescent tube, becomes unacceptable in a cosmological context? Why is that? Well, it has to do with these certainties that we collectively have around gravity being the only force and redshift being directly related to distance. Well, what if gravity is not the only force? What if electrical and magnetic forces play a critical role in the formation and structure of the cosmos? What if there is no such thing as dark energy and black holes and dark matter? What if we could take a step back from the standard model and look at the data with a fresh view? Well, that's not very likely, and it really has to do with the unfortunate human nature around reward stimulus and threat response. Now, some results from neurosciences have made their way into change management in business. And what has been found is that, and particularly around the area of reward stimulus and threat response, and what's been found is that we react in precisely the same way to a social threat as we do from an actual physical threat. Likewise, a social reward stimulates the same sort of dopamine response as an actual physical reward. So a threat to our certainty or our role in a social hierarchy is the same as a physical threat. Now, managing this perception of threat is described by the SCARF model, which uses 5 different domains to try to capture these different areas of risk and reward and threat response. So we'll look at these 5 domains in the light of workers within the lambda cold dark matter model and try to understand the different reward and the different threat responses. Well, let's go through the five different parameters. First, their status. This is our perceived importance relative to others. Now, mathematical and theoretical physics have enjoyed a certain status due to the glow it has from the intellectual kinship with the idolized Einstein. Now, as I've mentioned, the lambda cold dark matter model is a rather elaborate mathematical superstructure, and any threat to the underlying certainties of that structure will evoke a threat response. First of all, the reward stimulus is to retreat into mathematical formalism. That's a comfort zone. A threat response will evoke questions like, well, can you find any problems with our mathematics? Or, where's your math? But it's not about the math. Like the orbital velocity equation, there's nothing wrong with that equation. It's perfectly correct. The issue with it is the primary assumption that it rests upon, that gravity is the only force. That's the problem. There's no problem with the math. And there's certainty. Well, certainty is about our ability to predict. And one of the common threat responses to a threat to certainty is information gathering. And actually, it's been shown that gathering information is a very powerful reward stimulus and evokes the same sort of dopamine response as you get from addiction. It's basically an information addiction. So the kind of behavior you might see is the weighing of black holes, gathering information about how much this black hole weighs and that black hole weighs, or counting up black holes, or measuring distance through redshift. It's all information gathering. It's a comfort zone. The threat response would be pointing at rather extensive data sets as a means to shore up the certainty. But data sets are just information. They're not branded for any particular model or explanatory framework. It's just information that can be reinterpreted. Autonomy is about control and comfort zone, reward stimulus in this area would be computer modeling. So working with theoretical models of the universe in a supercomputer. It gives the workers more sense of control. A threat response here would be to point at evidence from the experiments in supercomputers. So showing the evidence from computer modeling, which is actually just based on the mathematics. Relatedness is about being part of a group. And the reward stimulus here is, of course, feeling like you are a part of a group. Threatening those certainties that I've been talking about from within a group, well, that means that implies a certain threat of being excluded from the group, which can be a very painful experience for humans. It also means that threatening those certainties from outside the group evokes a threat response around sort of an us-them language. And of course, that theories from inside the group inherently have more merit than theories that come from outside the group. It all has to do with relatedness. And finally, fairness. Everybody likes to be treated fairly, and it can help to attenuate the perception of threat by feeling you're being treated more fairly. But what does this all mean? What does this all mean? Well, it all means that asking these what-if questions, these dangerous, threatening what-if questions, evokes threat responses. And they're predictable threat responses, which include retreat into mathematical formalism and questioning of the math. Questioning of the math. The use of computer modeling to provide evidence that somehow shores up a certainty about the real cosmos. The pointing at extensive data sets, because information helps to shore up the certainty around the model. And finally, as a last resort, the emphasis on us-them language and depending on theories that come from inside the group. We are, after all, virtually unchanged from our tribal ancestors from tens of thousands of years ago, huddled around the campfire, and our reactions to social threat and reward stimulus is virtually unchanged. We struggle for certainty to ward off the darkness. And being intelligent, creative, insightful beings that we are, we have an immense capability to populate that darkness beyond the campfire with all manner of mythical creatures, or even sophisticated mathematical models. But I can't help from asking, what if? So, quite certain about, and that is the lambda cold dark matter model. Well, let's have a look at the lambda cold dark matter model. If you look it up on Wikipedia, it's a parameterization of Big Bang cosmology. The universe has a cosmological constant called lambda, which is related to dark energy. And there's cold dark matter. Now, between them, dark energy and dark matter comprise something like about 96% of the universe. It's unknowable. We can't interact with dark energy and dark matter. The other 4% is what we can directly interact with. It's a rather thin slice of the cosmological pie chart. But that's basically the standard model. The universe began in a big bang from a singularity, and from that, all the matter and energy of the universe originated. This was followed by a time of rapid inflation, followed by slower expansion. Cold dark matter, which we cannot directly interact with, constituted the framework for the subsequent bottom-up formation of stars and galaxies. And dark energy continues to drive this accelerated expansion. So let's begin actually with dark matter. Now, the cold dark matter model proposes that the universe is formed hierarchically from the bottom up, and smaller objects coalesce under self-gravity first and then merge in a continuous hierarchy, forming larger and larger objects. That's a basic premise. It's our dominant theory of the formation and structure of the universe. But there are observations that are actually very inconsistent with this proposal. One that I'm going to focus on is observations from January of 2013. This is from a group of observers from Canada and France at the Keck Observatory, who were amazed to find a group of dwarf galaxies moving in unison around the Andromeda Galaxy. They actually formed a thin disk-like structure. And since then, it's been confirmed that a similar structure is found around the Milky Way. So this is not something unique to the Andromeda Galaxy. In fact, it's a fair prediction that we'll find more of these types of disks of dwarf galaxies around other spiral galaxies now that we know what to look for. Now, it's important to recognize that decades of mathematical modeling of the cold dark matter theory in ever-increasing detail in ever more sophisticated supercomputers predicts that dwarf galaxies should be arranged randomly around the large galaxy. Well, actually, here we see 30 of these dwarf galaxies arranged in a solar system-like plane moving in unison around the Andromeda Galaxy, and this is true for Milky Way as well. So these observations are clearly inconsistent with the cold dark matter model. But the model persists. And the general consensus continues to be that dark matter is present, that the presence of dark matter in galaxies is nearly irrefutable. But why is there dark matter? If it's something we can't see, we can't interact with, and only seems to interact with the universe in a gravitational way, where does it come from? Why? Well, the need for dark matter actually arose in the late 60s and 70s from work from Vera Rubin, who plotted rotation curves like this for typical spiral galaxies. Curve A is what was expected given the mass density of the observed matter in the form of stars and dust. Curve B is what was actually measured. So what she found was that actually the stars orbited at around the same speed around the galaxy. This implied a much greater mass density further out on the galactic plane that could be explained by observable matter. So she proposed that there was something like 6 times or more the dark mass versus the observable mass. And very soon afterwards, it became fairly well accepted that most galaxies are dominated by dark matter. But there's a primary assumption at work here. In fact, it's explicit in the equation that's used to plot these curves. The equation for orbital velocity assumes that gravity is the only force at work. So as long as gravity is the only tool in the toolbox, then there's going to be the need for the ad hoc addition of some extra matter to sort of make up the difference. Well, let's turn now to redshift, the other primary assumption in the lambda cold dark matter model. Redshift. Well, by redshift we mean cosmological redshift, which is due to the proposed expansion of the universe. Light shifts to the red because of the expansion of the intervening space. So cosmological redshift is an indicator of distance. But actually, observations like this from Halton, Arp, and others have shown that high redshift objects can be in close proximity to, or actually physically associated with, low redshift objects. The quantity and quality of these observations preclude them being the serendipitous alignment of these objects in our field of view. There's something else going on. So you would think that observations like these would shake our certainty in redshift, but they don't. And our ongoing certainty about redshift as a cosmological yardstick will continue to yield surprising and unexpected observations of impossible cosmological objects. So let's look at a few of these impossible cosmological objects. There's impossible galaxies, impossible quasars. And they all have sort of a common theme. They're impossible because they're too massive, they're too energetic, they're too extensive for the redshift that they're at. They can't possibly have formed within the time that they had after the Big Bang, because being high redshift, they're much nearer to the time of the Big Bang, in theory. Well, let's look at one example. This is from a Hubble Ultra Deep Field, HUDF JD2, and it is far too massive at its redshift. At its redshift, about 6.5, it needed to form within about 800 million years after the Big Bang. And yet it's something like about 8 times the mass of the Milky Way galaxy. So there's a logical inconsistency here. Using that bottom-up hierarchical organization from the cold dark matter theory, how could it possibly have formed in that amount of time? So there is a retreat back to computer modeling and the supercomputers to see if they can make the parameters fit. There's another one. So this is BX422, which according to its redshift, needed to form within about 3 billion years of the Big Bang. Problem here is it's a perfect grand spiral design. It's too well formed to be possible at that redshift. So there's some more of those danger words: unexpected, impossible. Here's an impossible quasar. It's impossible because of its luminosity. At its redshift, it needed to form within about 900 million years after the Big Bang. Because of the assumption of distance being related to redshift, its luminosity needs to be extreme. It's an ultra-luminous object. In fact, if you do the math based on its proposed distance and its luminosity, it needs to be about 420 trillion times the luminosity of our sun. I'll just repeat that because it's a lot of zeros. 420 trillion times. So it's 7 times the luminosity of any quasar detected in the distant universe. Now, since gravity is the only force available to us to drive these things, it of course has, and other quasars, has supermassive black hole that provides the energy for it. So you see artists' conceptions like this of accretion disks around supermassive black holes, and it's a superheated gas. It's mechanically heated through gravitational forces of the supermassive black hole. Well, again, you do the math to get the energy levels that you need, then you have to get to a supermassive black hole that's 13 billion solar masses. So let's go back to the cold dark matter model again of the hierarchical accretion, bottom-up formation of matter, and it's difficult to explain a 13 billion solar mass black hole forming within 900 million years of the Big Bang. So you see that the primary assumptions lead to continued internal inconsistencies. Redshift equals distance. Well, if it's really far away, then it becomes extremely energetic. If it's extremely energetic, since gravity is the only force available to us, since it's the only force, you need supermassive black holes. But it's far away, so how can you form such a supermassive black hole when it's so far away and it's so close to the time of the Big Bang? It becomes logically inconsistent and will continue to break down. And more unexpected observations like this will be made. I should mention